Hello and welcome to the lecture Medical Imaging. In this lecture, we are going to understand the various aspects of medical imaging task like disease diagnosis, tissue segmentation, image synthesis, multiple instance learning, medical report generation, etc. Then, how deep learning models are applied for different medical imaging tasks, for classification, object detection, segmentation, etc. There are different tasks in medical imaging domain. For example, disease diagnosis, tissue segmentation, image synthesis, multiple instance learning, medical report generation. So these kind of tasks and many more is also possible are generally the task where the deep learning based automation is frequently used. To understand that how these architectures or deeper architectures are used for this task, first you have to understand what does this mean. What do you mean by disease diagnosis? By virtue of this statement we can understand we have to automatically diagnose some disease. Or can we segment? There is a given tissue, maybe CT or MRI modality or kind of plates, and we can find the segmentation. Then can we generate the synthesized or synthetic image in medical domain? Multiple instance means in a particular X-ray there is a different position or different objects or different region of interest. So in that way these instances are not labeled. Maybe labeling is done on the whole CT or whole X-ray. So multiple instance learning is that can we learn this? And automatic medical report generation is also a emerging phase. Can we generate medical report from a CT, plates or X-ray modality? So these are the problems where we are going to focus the learning strategies or deep learning models. But before that, we try to understand more technically what is this disease diagnosis, this tissue segmentation means. So disease diagnosis is basically in medical imaging task which primarily treated as classification task. So given some data, it may be unimodal, it may be multimodal, and our deep learning architecture is going to predict that a particular disease is there or not, or if disease exists, which grade it is. This may be a binary classification, this may be multi-class classification. Now here the deep learning model analyze images such as X-ray, CT scan, MRI to detect the presence or absence of disease. So these models automatically learn complex patterns and features that may not be easily visible to the human experts. So this is the disease diagnosis. Now, given our diagnosis, what are the trust factors? Or how can we say that whatever it is being given, that is truly okay? So here is the trust in these findings are confirmed by few things. That's called GradCam. It highlighting the regions in an image that are most important for the model predictions. So this GradCam is basically going to say, look, there is a problem there. And TNSE plot, that projecting the high dimensional feature embedding to a low dimensional space, by which we can also understand. So this is somewhat the disease diagnosis. Next come the tissue segmentation. Given this kind of MRI slice, can we segment? This is the ground truth, and this is the automatic way to segmenting this. Can we get some images or automatically? That is very close to the ground truth. So the tissue segmentation in medical imaging refers to the process of dividing an image into meaningful regions. Okay, so this is the such as organs, tissues, or abnormal structures like tumors. It is typically formulated as a pixel-wise or voxel-wise classification task. So kind of segmentation, kind of semantic segmentation, pixel-wise classification for the medical image, where each pixel is assigned to a level corresponding to a specific tissue type. What are the major challenges here? That unclear boundaries, edges between tissues is not always very clear. High anatomical variability across patient. There is a different kind of variability. It is not that for a similar disease, different patients has a different kind of variable autonomic anatomical differences or heterogeneous anatomical signatures. So limited annotated data. That means this data is not very easily available because this annotation require medical person or medical personnel involvement and is very costly. So pixel level leveling is expensive. Okay, so this is the problems and how we'll see deal with it. Then medical image synthesis. Medical image synthesis is basically what? That it synthetically generate images or given a modality, can we get another modality? So medical image synthesis involves generating one type of medical image from another using a deep learning model. For example, generating MRI from CT or high quality images from low dose scan. There is a kind of smaller X-ray devices. So can we get the standard X-ray plate or X-ray images from this kind of smaller devices? So this helps reduce radiation exposure, improve image quality, enable multimodal analysis when certain modalities are unavailable. Okay, so this medical image synthesis is very, very important nowadays. What are the challenges we generally face in this domain? Preserving anatomical consistency. That is very important. Given MRI, when you convert it to the CT, that this anatomical finding should be same, and that is very tough. Lack of perfectly paired data set, that is also important. Same patient, same problem, CT as well as MRI. These pairings is costly, or it is there is a scarcity of this pair of images. Evaluating realism and clinical reliability, that is also important. A clinical reliability and realism is very much subjective. So this is another domain where we can put deep learning models. Now multiple instance learning. It is MIL is training sample is a bag. Now the whole medical image. So there is a let's say it's a CT scan, and it contains multiple instances or image patches or regions. Okay, labels are only provided at the bag level, that a particular X-ray is okay, this is diseased, this is normal, but never said which portion is abnormal and other portion is normal. That information is not there. So labels are only provided at the bag level, and the task is to learn from these to make both bag level and potential instance level prediction, and that is quite challenging. So positive bag, at least one instance is positive. A negative bag, all instances are negative. So CT, MRI, volumes, histopathology. So this is called multiple instance learning. How we proceed? Bag of instance means that there is a k instances, where xk is equal to real space, kth instance. Number of instance per bag may vary across samples. That is also possible. So in standard formulation, the instances of a bag exhibit neither dependency nor ordering among each other. Okay. So what we are to do is further assume that binary instances exist but are not necessarily known. So binary bag level is 1 if and only if at least one instance level is 1 to this. So what we basically do, this is the images. Okay. So patches we get, then feature being detected and the feature extracts, and then classify positive or negative instances. So this is another way of. Another very important thing is called medical report generation, automatically. So it refers to automatic creation of clinical or diagnostic reports from medical data using artificial intelligence or machine learning techniques. Input is medical image, maybe X-ray, MRI, patient records or sensor data. Output a written report that describes the findings, diagnosis or recommendation. Just for example, no sign of pneumonia or fracture history. Now this given these images. Finding the 3 images are available for review. So, and this is the review. The heart size is normal, the mediastinal contour is within the normal limits, and so on. Maybe it is given 3 images and this finding. An impression, no acute radiopathic cardiopulmonary process. So this kind of report can be generated automatically. Now we'll give just a kind of small ideas, very hypothetical. It is not that taken from a paper, but it's very hypothetical. How did, because there's 2 models, it is on text model, it is on kind of X-ray or MRI or CT, whatever image modality. So ground truth report register is the first way into the text encoder to obtain the semantic representation extra. So this. The visual feature extracted by the image encoder and passed through a contrastive learning and subsequently input to the text decoder to generate the report. So this is the visual. So it use contrastive learning. Contrastive learning means what? That if they are alike, then it will cluster. If they are not alike, they cluster in a different position. So we cluster the similar points and make the distance with the different points. So here this is done by this. It's text encoder and this is image encoder and contrast between this. And this is a text decoder that will give this. Basically this formulation, that there is some sort of reports. The text decoder generate the report T. And in traceback mechanism, so this mechanism, the generated T is reintroduced into the text decoder, okay, a text encoder to derive its semantic representation XT. So this XT, and they can find the semantic loss. So how good it is being treated. The discriminant XT star and XT to as the semantic loss and used to object function for the traceback process. So this loss is minimized. This mechanism designed to minimize the feature level difference between generated report and the ground truth register, thereby improving the semantic consistency. So this is a kind of hypothetical way to do medical report generation. So here there is a 3 alignment kind of methods. The global alignment, where the overall representation if modality is captured, the spatial token, the CLS token, enable the alignment at the global level. Middle local alignment, which focus the fine-grained matching by analyzing or aligning the individual image patches with corresponding word tokens. And right alignment via intermediate matrix means where a sphere representation matrix is learned to encode feature for both modalities, ensuring the map into the same reference space. Basically, these are the basic alignment techniques. How do we align these two? These are two modalities. Somehow we have to align it so that we can get a fused paste, or we project in a kind of fused paste. So this is the way. Okay. Now, what we have to understand, how the deep learning models are being utilized in medical imaging. Now, there is some different perspectives. First, the practical perspective, that to help the medical professionals for dependable medical assistance. If you go by the research perspective, that the medical images involve visual and latent information of disease biomarkers that can be traced using deep learning. So there is a different, the academic perspective, then that is a research perspective, some sort of practical perspective. So what are the basic tasks? What we have seen? Disease diagnosis, lesion, organ or abnormality detection, tissue segmentation, medical image synthesis, medical image retrieval, medical report generation, so on. That we have shown in last few slides. And what are the challenges? Medical images are grayscale in nature, have non-differential spatial context, and often contain small region of interest compared to the image levels. So as you can see, this is the OCT image and this is the MRI image. Another important thing that we are generally face, that the labeled or annotated medical image is very costly. So now we have to think that how this kind of problems are solved. Now, one thing we have to understand, medical image is a particular field. Medical images have some typical characteristics, maybe X-ray, maybe MRI, maybe CT, maybe others, biomarkers or some tabular data. So it's a multimodal kind of environment. So medical imaging, when we use deep learning, it may be unimodal thing, or it's a multimodal thing, or sometimes it is one model to another model, image synthesis. So one thing is very important to understand here, that the typical vision task like classification, object detection, semantic segmentation and so on, these tasks, how it is being involved in medical imaging, and our perspective or our notion of understanding towards this ability, that we are going to understand how the classification, the normal classification being used or being utilized in medical domain or medical domain modalities, how semantic segmentation, how object detection, and so on. Let's start. So first we have to understand the training pattern of the medical images. So First is feature learning. Now feature learning is basically is that, as we have said, that number of leveled images may not always be very high. So generally one thing that we generally practice, we take a pretend image or pretend model. That is some convolution layer. This is decant. Let's say for just let's pretend network. Let's say VGG, or let's say Google Net something, or imagine it is pretend of this. There's a huge data set in this pretend model, and it can use this dog, cat, this kind of tree is very well. Now we use the transfer learning on this pretend network. So two things can be done, two ways it can be done. That is, one is this, that medical data set, this feature what been extracted, the extract feature from the target data set, this in that basically this in this pretend network, this medical data set, we get some feature and it put it to the linear SVM and softmax to get our diagnosis. Another way that we have this particular retained FC8 or some higher layers, and then we train the next layers on the basis of this medical data. This is fine tuning on the data set, and we get this classification. So basically feature extractor based, and another is fine tuned. These are two major way of doing this. Okay. Now first we have to understand how we do the classification. Now we are not going to in very in depth. This is a recent paper and in 2021 paper. We are not going this is the basic idea, is that we are not going to understand it is in entirety. Rather, we try to understand the basics way. So this is not a research level course, it's just academic. So training deep learning model with disease specific descriptors, how it is basically being used. So fuse TSD, it full form is fuses the texture, shape and deep model learning information. Basically this algorithm is being used. So you can see there is a 4 basically the steps. First 4 major steps: extracting the nodule region of interest RY from each chest CT slice. So this it basically that is the nodule region interest RY from G, to extracting the nodule region. If there is any nodule region, so that can extract this. Then training a deep convolutional neural network for deep feature extraction and extracting texture and shape features. Okay, after getting this RY thing, this is feature extractions. There we see. Then this using each feature type, train a AdaBoost backpropagation neural network that basically is this feature, this feature, and this. And finally estimating the way of each AdaBoost fuse the classification. There is some fusing to get this. So this, the internal dynamics is not that much important. What is the overall way to doing this of this kind of deep architecture? This is the interesting way on. That is what we understand. Next, this is basically the same thing. that the online testing has this was the training part. Now the testing time, extracting the nodule ROI from each slice of the to be tested nodule, applying ROI to the trained DCNN to generate its deep feature, or the same thing. Applying deep texture and shape feature to trained ensemble classifier is, and classify the nodule based on the level. And this is the basic way of doing this. So this is the way to do classify. So the classification is done in this way. Then a hypothetical example that we've taken from a very recent. Okay. Next, another technique. This architecture is called LSCN. Okay, the lesson-aware convolution neural network. So, what does this mean? What basically it is doing? The LSCN is constructed by a series of lesson attention modules. Lesson attention modules. There is a pooling and convolution in between, but this lesson attention modules. And then convolution layers and pooling layers in between. In each lesson attention module, the feature maps from previous convolution layers and attention map from DN are the inputs. And lesson aware feature maps are the output. So this is the lesson detection. LDN means lesson detection network. So this is the way. This is the another. Next thing is object detection. Now, utilizing images under different setting, multiple views or modalities, or analyzing the adjacent slides for the computer vision task. So, how the object is being detected in a medical image? So, in order to model the domain knowledge and human expertise, the MVPNet, what is the full form? Multi-view FPN with position aware attention. Okay, for universal lesson detection is developed. So this is a paper. The how we are doing. So first of all, you have to understand what is the feature pyramid networks, FPN. This is basically a building block of improve the detection performance of small lesson. To leverage the information from multiple window instruction, a multi-view FPN is built to extract the multi-view features using the three pathway architectures. So here you can see that the three pathway convolution. So there is the three input images, the three different modalities, and we can get it. Okay. So then a channel-wise attention module is employed to capture the complementary information across the different views. Right. Okay. So this position awareness modeling. So this is the another way of doing object detection. But next, okay, that a deep network called the contrasted bilateral network (CBN) is developed for a automated mammogram mass detection. Okay, so this is the. So how it is being done? These are the aligned images. These two. And backbone features, they are basically the feature map, and then feature map, this is an RPN. Okay. Motivated by the domain knowledge that radiologists read mammograph images, the bilateral information is integrated to the model explicitly and tackled two important problems along the way. And what is important? To find the corresponding region in the contralateral image registration as an image level solution, firstly applied to map bilateral image into the one coordinate system. So there is two things: mask head, the object detection, and the box head. Okay. So what is the basic idea? Moreover, the distortion intensive comparison specially designed to tolerate the non-rigid distortion of the bilateral images. And to further boost the performance, the inherent logic is analyzed constant to the way that radiologists read images and propose the logic guided bilateral models. The overall pipeline can be integrated smoothly to a mask RCN framework and front-end. So these are the basic idea of this particular object detection. Now we are going to discuss how segmentation is implemented in medical domain. So this is a typical paper or typical work, that is enhanced DNN model with shape reconstruction and spatial constraint SC. This name is SRSC. Is developed to tackle the challenging segmentation task, particularly with a small set of data. So here you can see this is unit like of okay. So this is segmentation that we can get the segmentation. So the overall structure of SRSCN, whose loss comes from the three parts: the segmentation loss, a specially designed function of cos entropy and Dice loss, and spatial constraint SC loss to assist the segmentation, and the shape reconstruction loss, the shape repolarization. Okay. So this is the main three losses. The resulting network is expected to be able to constrain the segmentation to generate a result with a realistic RCN. The shape reconstruction neural network, this SRNN, is proposed. This SRNN can be trained by anatomical priors such as a set of level images, and it works as a shape constraint to regularize the result. And hence, SRNN can maintain a realistic heart shape of this result. So this is some sort of idea of segmentation. So this is because that 2D slices may come from any position. Okay. The shape and the appearance of these slices can vary considerably. That major problem. The SCN is designed to incorporate this information. So by combining these two, the learning task of spatial information with the problem and the formulating them as a two-task learning problem, one can expect that SCN to significantly improve the general performance of the network, opposed to the separate training of the two tasks. So here we can say that basically the virtue of three losses, this segmentation. It is not required to understand the full basically the architecture, because this is the research concept. But the main agenda here, the main goal to how a segmentation being implemented is in paper, the virtue of these losses and in this unit architecture. Okay. So in summary, in this lecture we have discussed medical imaging tasks like disease diagnosis, tissue segmentation, synthesis, multiple instance learning, medical report generation, etc. And then within how the classification, object segmentation implemented by virtue of deep learning in the medical domain. This next we discuss zero shot learning. Thank you very much.